Welcome to Elementary Real Analysis. Today we are going to explore Cauchy's nth root test, a powerful mathematical tool that helps us determine if an infinite series converges to a finite number or blows up to infinity. This concept is foundational for understanding how infinite sums behave, and by the end of this video, you will know exactly how to apply it. Before we look at the math, imagine building a tower with an infinite number of wooden blocks. If all the blocks are the exact same size, your tower will grow forever and eventually crash through the ceiling. This represents a divergent series. To keep the tower safely inside the room, each new block you add must be significantly smaller than the previous one. Cauchy's nth root test acts like a strict building inspector. It checks the shrinkage rate of your blocks to guarantee whether your infinite tower will fit in the room or if it will inevitably crash. Now that we understand the goal, let us look at the mathematical formula. The test requires us to calculate a limit, which we call L. We find L by taking the limit as n approaches infinity of the nth root of the absolute value of the nth term. The absolute value ensures we only deal with positive quantities. The nth root essentially asks what number multiplied by itself n times gives the value inside. If the resulting limit L is strictly less than 1, the series converges. If L is greater than 1, it diverges. If L equals exactly 1, the test fails completely. To make this even clearer, let us visualize the three possible outcomes of our test using a decision flowchart. As you can see on the screen, everything starts with calculating the limit L. From there, the path splits into three distinct directions. The green path on the left shows that an L value less than 1 leads safely to absolute convergence. The red path in the middle warns that an L value greater than 1 leads to divergence. Finally, the gray path on the right reminds us that getting exactly 1 means the test is inconclusive, forcing us to try a different mathematical tool. With our rules established, let us see this test in action with a concrete example. We are asked to determine if a specific infinite series converges or diverges. Notice that the entire nth term is raised to the power of n. This is a massive clue that the nth root test is the perfect tool for the job because the nth root will beautifully cancel out that nth power. We start by identifying our nth term and then we plug it into our formula by taking the nth root of its absolute value. Continuing with our simplified expression, we now take the limit as n approaches infinity. The nth root and the nth power have completely cancelled each other out, leaving us with a simple algebraic fraction. To evaluate this limit, we divide the top and bottom by the highest power of n, which is just n. As n gets incredibly large, the fraction 1 over n shrinks to exactly 0. This leaves us with a final limit of 1/2. Because 1/2 is strictly less than 1, our test guarantees that this infinite series converges to a finite, manageable number. Now that we have solved a basic problem, let us tackle a more intimidating series involving exponential limits. Here, we have a series where the term is raised to the power of negative n squared. While it looks complex, the presence of n in the exponent tells us to use the nth root test. Because the term inside the parentheses is positive for all positive integers n, we do not need to worry about absolute value signs. We simply apply the nth root to the entire expression, which is mathematically the same as raising it to the power of 1 over n. Moving forward with our calculation, we can simplify the exponent. In algebra, when you raise a power to another power, you simply multiply the exponents together. So we multiply negative n squared by 1 over n. This simplifies beautifully, leaving us with an exponent of just negative n. We have now reduced a very complicated expression into something much more manageable. To make the next step easier to recognize, we can rewrite this negative exponent as a fraction, placing the positive version of the expression in the denominator. Now we evaluate the limit of this simplified fraction as n grows infinitely large. The expression in the denominator is actually one of the most famous limits in all of calculus. As n approaches infinity, it defines Euler's number, the mathematical constant e, which is approximately 2.718. This means our final limit L is exactly 1 divided by e. Since 1 over e is roughly 0.36, which is strictly less than 1, Cauchy's nth root test guarantees that this complex-looking series safely converges to a finite sum. We have successfully used the formula twice, but why does this test actually work? Let us prove the first case, where the limit L is strictly less than 1. We cannot just accept a mathematical rule without proving it step by step. The intuition here relies on comparing our complicated series to a much simpler, well-understood geometric series. If our limit L is less than 1, we can pick a specific constant fraction. Let us call it r, that sits right between L and 1. Because the limit approaches L, eventually the nth root of our terms will be strictly smaller than this chosen number r. Continuing our proof, we remove the nth root by raising both sides of our inequality to the power of n. This reveals that the absolute value of our term is strictly less than r to the power of n. This is a massive breakthrough. The expression r to the power of n represents the exact terms of a geometric series. Since we specifically chose r to be less than 1, we know for an absolute fact that this geometric series converges. Because our terms are always smaller than the terms of a convergent geometric series, our series must also converge. This completes the proof for the first case. So, we have proven that the series converges when L is less than 1. This brings us to the second part. What happens if the limit L is strictly greater than 1? If the limit of the nth root is greater than 1, it means that eventually, as we go further down our infinite list, the nth root of the absolute value of our terms will be strictly greater than 1. Mathematically, if the nth root of a positive number is greater than 1, then the original number itself must also be greater than 1. Let us write down this crucial inequality. Looking at this simple inequality, we see a major problem for convergence. The terms in our series are actually larger than 1, meaning they are not shrinking to 0 at all as we move further down the list. There is a fundamental rule in mathematics called the necessary condition for convergence. It states that for any infinite sum to equal a finite number, the individual terms being added must eventually shrink to exactly 0. Since our terms are staying larger than 1, they are completely failing this basic requirement. Therefore, adding them up forever will inevitably result in infinity, proving that the series diverges. Now that we have proven the mathematical foundations, let us understand where this is used in the real world. Why do we care about Cauchy's nth root test? In advanced mathematics and physics, we frequently encounter power series, which are infinite polynomials used to approximate complex functions like sine waves or exponential growth. The nth root test is a primary tool for finding the radius of convergence, which is the safe zone where these mathematical approximations actually work. For example, in electrical engineering, if a series modeling a signal diverges, the model predicts infinite energy, meaning the system would physically explode or fail. To wrap up our lecture, let us review the most important ideas we have covered today. Cauchy's nth root test is a powerful diagnostic tool for infinite series, especially those involving nth powers. By taking the limit of the nth root of the terms, we find a crucial ratio L. If this ratio is less than 1, the series safely converges to a finite number. If it is greater than 1, the series uncontrollably diverges to infinity. You have now mastered both the application and the proofs behind this essential mathematical tool. Great job following along with these complex concepts.